substituted benzene, right? So under dienes, we are going to learn about the types of dienes and the reactions of dienes. And then we'll talk about what aromaticity is and the Heukel's rule on aromaticity. And according to the Heukel rule, we can divide aromatic compounds as, divide all the compounds as aromatic compounds, non-aromatic compounds, and anti-aromatic compounds. So then we'll study the reactions of benzene and the reactions of some reactions of substituted benzene under these topics, right? So let's see. Let's start our discussion on diene systems. So you can see there are, sorry, I missed explaining this. There are several types of dienes. So these are the four possible types of dienes that can exist, right? So this is isolated diene system. You can see the double bonds are far apart. You have the double bond and several single bonds and then the double bond. So that is called isolated double bond. And this is called isolated but skipped double bond. You have the double bond, two single bonds and a double bond again. That is called isolated or skipped type. It is isolated but skipped, right? And this is a conjugated double bond. You have a double bond, single bond, double bond, single bond. Alternating. Bonds are double and single bonds are alternating. That is called conjugated double bonds. And this is called cumulated double bonds or allenes. These type of compounds, carbon with 4 bonds, two carbons are called allenes. Then under the addition reactions, we will be studying 1,2 addition and 1,4 addition, and another type of another famous type of reactions undergone by dienes are the Diels-Alder reaction, right? So let's see the stability of dienes. You can see 3 types of. Now this is an allene. Hope you can identify those. What is this then? Just now I told you this is a allene. Double bond, single carbon has 2 pi bonds, right? It is an allene, and this is a skipped double bond, and this is a conjugated double bond. So number of carbons on the molecules are the same, and number of double bonds are also the same. So look at the heats of hydrogenation of each of these different types of dienes, right? You can see here it is minus 295. And this is when you go down, you can see the heats of hydrogenation decreasing. And what can you say? Now heat of hydrogenation means hydrogenation of the diene system, right? So it can be done, you know, for your level 3, you have studied in the presence of a catalyst like platinum, nickel, or palladium, you can hydrogenate, right? So when that hydrogenation is taking place, the heats of hydrogenation, the amount of energy released is discharge. Energy release when the total reaction is taking place. So the lowest energy, the amount of energy is lowest when hydrogenation of this conjugated double bond system is taking place, right? So why? You can see here it is little above, and in this one is very high. The released energy is very high. So you can see the final product is the same, and only difference is in the diene system. So when it comes to that, goes to from bottom to top, the energy of the starting material is high. Lowest energy is shown by the conjugated system. So that when it becomes this product, the difference between the energy of the starting material and the product is less here, right? Product means it is obtaining more stability so that it releases energy. So the energy difference is lowest here because this is more stabilized. And the conjugated diene system is the most stable diene. So hope you understood what is happening here and the reason behind. Okay, so if you have any questions, you can ask, right? So considering the following compounds, explain why conjugated dienes are more stable. Can you think why? Can somebody give me an answer? Now I have uploaded my presentation also, and by now you have to go through your course material and understand the things.
Well, because mainly when it comes to conjugated dienes, more stable is mainly because there's an alternating single bond, double bond, single bond, double bond between each other.
Yes, you can see it here. So then what?
So because if that when it comes to the single bond between the CHs, in located on the right and left sides is a double bond belonging there.
Yeah, you can see the structure here. They are partly correct, but you didn't give me the exact reason why it is stable.
There
right?
can be a partial double bond forming between C2 and C3.
Yeah, because this compound is showing resonance stabilization. Resonance stabilization takes place by the movement of the pi electrons throughout the molecule. So it can happen like this. So your answer should include this word, resonance stabilization. So resonance stabilization is taking place the way I have indicated here, right? Either these pi bond electrons on the pi bond can move like this, so that you get a resonance structure like this, where you have a positive charge on this carbon atom and a double bond created in the middle and negative charge on this carbon. Or else it can happen the other way, because it has the freedom to move its electron the other way around the molecule, right? So when it happens, you get a positive charge on this carbon, double bond in the middle, and in the terminal carbon atom, you get a minus charge, right? So when you compare the two resonance structures, this is more stable. Why? Can you give me the reason? Positively charged, it is more stable because positively charged carbon atom is stabilized due to the electron pushing effect of the CH3 group, alkyl group. You can see an alkyl group is attached here. You know, alkyl groups, by definition, we know that they pushes electrons, right? So it pushes electrons like this, right? So when it pushes electrons, the negative charge is partially neutralized, like it gives electrons. So the positivity of this carbon atom is less in this case. Whereas it doesn't happen here. It has only this group R. Of course, this the carbon has two groups to show, which show plus I effect, electron pushing mesomeric effect. We call it electron pushing mesomeric effect. In this case, you have only one alkyl group to neutralize the positive charge on carbon atom. So that the second one is more stable, right? Okay. So as I said, the important
Excuse me.
Yes.
Yeah, in the previous slide, can we say that primary carbocation and the secondary carbocation by comparing?
Yeah. That is the reason I didn't mention the two words. This is a secondary carbocation. This is a primary carbocation, right? Primary carbocation has only one alkyl group. Secondary has two groups. So that secondary carbocation is more stable.
So can we use that?
To give you more understanding, I have put it that way. You just can say this is a secondary carbocation and it is more stable, right? Okay. So let's see the 1,2 and 1,4 addition reactions of these conjugated dienes. Now you are very familiar with this reaction, HBr addition to alkenes. You have studied at level 3, right? Hydrogen bromide addition to alkenes. So if the addition is taking place in this way, addition to C2, that means you can see the hydrogen is added to this carbon atom and the C2 position, and bromide is going to get attached to C1, right? So that reaction does not take place because through this mechanism, you are going to get a primary carbocation which is unstable, less stable. when you have to compare with the other one, so that when you compare, this is less stable, whereas in the second one, when the addition is at C1, it is secondary carbocation, right? So the secondary carbocation has two resonance structures, which show resonance stabilization and more stable, right? And these two resonance structures can separately undergo addition. So if this secondary carbocation undergoes addition, it will give you 1,2 addition product. We call it direct addition, right? And if the other resonance structure undergoes the HBr addition, it gives 1,4 addition. You can see why it is called 1,2. So 1,2 is first carbon atom is this, second HB hydrogen is here, Br is here. In this case, hydrogen is here and Br is attached to the C4 carbon atom, right? So that it is called 1,4 addition, and we call it conjugate addition also. And when you do the reaction, actually, when you perform this reaction at 40 degrees centigrade, you can see more of this 1,4 addition product is present in the reaction mixture. And the 1,2 addition product is 20%. These are rough compositions. But anyway, what we want to show you is you get 1,4 addition product more when the reaction is happening at this particular temperature, right? So reason for this this temperature conditions, the reason for becoming this product more is this compound. It shows on the carbons of the double bond or the double bonded system is sp2 carbon atoms, right? This here you have the double bond, and they are more substituted. You can see the double bond is substituted here, 2 groups here, whereas you have only 1 group substituted. So when you have 2 groups substituted, it is more stable. Understood? So at this temperature, now note the temperature here, right? So we will get different compositions when the temperature is changing, right? So we can show why it is happening by plotting a free energy diagram like this. Now, when the reaction is taking place like this, 1,2 addition product is this one, and 1,4 addition product is this one. We call this 1,2 addition product the kinetic product. This amount of the kinetic product is there, but it is formed rapidly, but less stable. Less stable due to the double bond is less substituted, right? But it is formed rapidly. Why? You can see when the reaction is taking place like this. Now, this is the plot or the graph for the reaction. You can see it goes through a intermediate like this, and then the transition state like this, and the intermediate is here. So when the intermediate is when the kinetic product is formed, it is more stable, less stable. The product is here, but the activation energy for the kinetic product is less. So this delta G2 is less here. Whereas for the thermodynamic product, it is more stable due to more substituted alkene, because it is going to give you the more substituted alkene, but the activation energy is more here, right? The forming the carbocation, the resonance, the carbocation is having a higher activation energy, so that it has to exceed that when the intermediate is having that the sufficient amount of activation energy of delta G1, it will undergo this reaction to give you the thermodynamic product. So when you are doing the reaction at 40 degrees centigrade, that energy is sufficient. It is enough, energy is enough to go through this stage, so that you get more of this one, because enough energy is there to give the thermodynamic product, which is the most stable, right? So I have to say one more thing when you are drawing. So a little while ago, before I start this day school, I was going through your papers, marking some papers. So you are not very clear when you are drawing a plot like this. There was a question where you had to draw the energy diagram for SN1 reaction. So here, most of you have put it as just energy. Even then I have given mark. This should be free energy or Gibbs energy or something like that. Just energy is not enough. Anyway, I have given marks. And this axis is progress of reaction, right? Not time or I don't know, so many different unacceptable, even process of reaction. Even for that, even sometimes I have, no, for the process I didn't give progress of reaction progression. This axis shows the reaction progression, right? So be careful when you are looking at a graph, you learn what the axis, how the axes are labeled, right? So those are also important. So when we are giving marks, we give marks for each and everything, for the axis, the shape of the graph, the energy of the starting material is, and energy of this reaction will not take place if this delta G is not negative, right? You have to have the starting materials at higher stage and products at a lower. Sometimes some people have drawn the products here, which is very wrong, right? Okay. Right. So this is another way of asking another question based on the same phenomena, same addition reaction, but note the temperature is different here. When the temperature is minus 80 degrees centigrade, you get more of the 1,2 addition product. And 1,4 addition product is less. Why? You should be able to explain now. Tell me why. It's over, but I need the answer.
Now when it comes to percentage more, when the reaction is okay at 80 degrees Celsius,
Minus 80.
I mean minus 80 degrees Celsius at the cold temperatures, definitely it will yes, because this conjugated thing means that the bromine will be attached on top, on the bond break.
Okay,
And
yes, partly correct. Now, at a lower temperature, you don't have enough energy to overcome that activation energy of this 1,4. You saw 1,4 product has the intermediate transition state and needed higher energy. So that this temperature is not enough to overcome that barrier. So that kinetic product is more in that case and the thermodynamic product is less. So partly correct, right? Okay, so someone have put the answer in the chat. It is correct, right? Okay. So this was one of the example past paper questions, right? So again, I have another question. So I'm not going to give you the answer. Answer is question is from the book itself. Now with the knowledge you have, you should be able to explain this, right? Okay, let's see the reactions of dienes. So as I told you, 1, 2, and 1,4 additions we have now discussed. And the other famous type of reactions these dienes undergo is Diels-Alder reactions, right? So it's very easy. You can see electron migration transfer takes place like this. This is called the diene system, where you have 4 pi electrons, right? You have 2 pi bonds. And this is called the dienophile. Phile means likes or loves. Dienophile means this species loves a diene or likes a diene. So this can donate electrons like this, and electron transfer takes place in a circular manner like this in a ring, and giving rise to a ring structure like this, right? Dienophile has 2 pi electrons, right? So this reaction takes place at higher temperatures and high pressures, right? And you can see when the movement is like this, you get a double bond created between these two carbon atoms. And these two bonds are newly formed, right? So it's very easy. I have a question. We have two questions. Actually, this dienophile is a triply bonded compound. Same way, electron migration can take place. So can you all write the answer for the first part? So several examples are there in the book, right? You just have to draw the electron migration. You just ignore the constituents, the substituents attached to this carbon atom, because this diene system is a symmetric system. When the diene system is not symmetric, like this, like the example given in the number 2, then the problem, right? So if you have a symmetric system, no problem, you can put the migration, the arrows, the way I have shown you earlier. So let's move. Okay, have you all tried at least? Okay, so many examples are there. So you just have to move electrons like this, or even other way around. It doesn't matter. You put the arrow from this end to this end, even okay. Then the other arrow should be here, and the next third arrow should be from here to this carbon atom. So you will get a two newly created bond formation and a substituent here, right? And if you have two systems like this, when the dienophile and the diene are substituted, right? And that means due to the substituents, this dienophile, this is the dienophile, and the diene can acquire resonance stabilization. So you have to consider the resonance structures of the diene as well as dienophile when you are giving the writing the product. So in this case, it's a little tricky. Now in this diene, you have a OCH3 group attached, so that the non-bonded electrons can move like this to give you a transition state, not the transition state, resonance state like this. And same way, this dienophile also can show resonance like this. So that you can see now these electrons cannot be donated here, because you have a electron rich place here and an electron deficient place here, so that they can get bonded easily. You donate this end, donates electron to this positive end, right? So when electrons are donated here, then only the circular manner the electrons transfer can take place. So it is this way the electron migration is taking place, so that you will get a product like this, where you have OCH3 group here, and next carbon atom has the CH3 group. Otherwise, we expect this to be somewhere here, right? Here. It's not happening. So. Okay, so. Right, so hope you have understood. So, as I mentioned, several more examples are there in the book, right? You go through each and everything, so you can get the idea better, understand it better. Okay, so let's move on to aromaticity and the Heukel rule. What is aromaticity? Actually, there are different ways of describing what aromaticity is. This is one way of giving the explanation. It is the enhanced thermodynamic stabilization by cyclic, planar, or near planar. Can be planar or near planar. Almost planar. Near planar means almost planar, but not really planar molecules, right? So enhanced thermodynamic stabilization by cyclic and planar molecules. They show resonance stabilization due to delocalized cyclic pi electron systems, right? They have pi electron systems, and they can be delocalized, and they show properties which are similar to benzene. So you know what benzene, our next slide is on benzene. So all the aromatic compounds show properties which are similar to benzene, right? They show resonance stabilization due to delocalized cyclic pi-electron systems. And they have acquired extra thermodynamic stabilization due to this delocalized cyclic pi-electron system. So what is Heukel rule? We are next going to learn what Heukel rule is. It is a rule to predict aromaticity of cyclic conjugated dienes. So cyclic conjugated dienes of this nature: monocyclic, planar, and delocalized pi electrons in a closed shell. Delocalized, the number of delocalized pi electrons should be fitting into this formula. This number 4n plus 2. Number of pi electrons should be 4n plus 2. N is an any integral, maybe full number 1, 0, 1, 2, 3, like not half numbers, right? Full integral numbers, right? So you can apply this Heukel rule to systems which are monocyclic, planar, or and planar, and this number of electrons are there. You can apply Heukel rule. That is the Heukel rule for aromaticity, right? Monocyclic, sometimes you get some deviations. When it comes to monocyclic, there are some compounds which are aromatic. They are not really monocyclic, but they have an outer ring. We can consider the outer ring as a cycle system where the cyclic conjugation is there. We will come across several examples in next few slides. Okay, so this is benzene. You are very familiar with this one. This is what we draw on paper, right? You draw a flat structure, 2D structure of this one, but actually it is like this, right? You have on each carbon atom, there are 6 carbon atoms. On each carbon atom, you have a empty p orbital, right? So the electrons, each p orbital has one electron, that then all 6 pi electrons are forming a cloud or a ring structure like this above the plane of the molecule. These electrons are circulating in a ring line, right? So it is monocyclic, and when you actually make the structure using stick and mold models, you get a planar structure, and this number of pi electrons are 6. Each p orbital has 1 electron, so number of pi electrons are 6 in a closed shell. Closed shell means it can freely move right around the ring, right? So we call this, all these carbon atoms are sp2 hybridized. Though we write a structure like this, confined this double bond confined to 2 carbon atoms, it's not really happening. What happens is there are no true double bonds in the structure. These electrons are common to all 6 carbon atoms, so that these 5 electrons moves right around the ring. So I can remember when I was learning about benzene, when I was doing my A-levels, I had a famous teacher. Actually, she's Mrs. Selvaratnam. She is the wife of a famous organic chemistry lecturer, Mailu Selvaratnam, who had written a organic chemistry book in Sinhala, Carbonica Rasayana, right? So Sinhala is not that good. We studied in Sinhala. Mrs. Selvaratnam Sinhala is not that good. So she used to explain this like electron rasti adugan, ring ekavate rasti adugan. So you get the clear idea when you get this word, when you know this word. Rasti adugana means it in a closed shell line, right? It doesn't go outside, but in the ring, it is going round and round, right? So you get the idea clearly when you have this word, right? So I used to have the clear idea when I heard this word, right? So these 6 pi electrons are circulating right around the ring, and we call it a closed shell. So benzene obeys Hugel rule. It is monocyclic, one ring, a planar. Actual model is a planar structure, and it has 6 pi electrons, which obeys this Hugel number. It is 4n plus 2 when n is 1. N can be any number, right? So when n is 1, 4 into 1 is 4. And when you add 2, you get 6. So it is the Hugel number. So benzene obeys Hugel rule. And if any compound which obeys Hugel rule is going to be aromatic. So hope you have understood. So though you have written the structure like this with all carbon atoms sp2 hybridized, remember these are not true double bonds. That is why benzene is not showing reactions of alkene, right? If a benzene is having 3 double bonds like this, it should show it should undergo alkene reaction, but it's not happening. Benzene is showing different reactions, undergoing different reaction, because it is showing aromaticity, not an alkene, right? Okay. So let's see the requirements for aromaticity, and depending on the amount of these requirements fulfilled, we can categorize compounds as aromatic compounds, anti-aromatic compounds, and non-aromatic compounds. So let's see how we are considering, or how we are using this criteria to define aromatic compounds, anti-aromatic compounds, and non-aromatic compounds. So in aromatic compounds, you have a cyclic system. Remember benzene. Take benzene as an example. When you are thinking of aromaticity, the best example is benzene. It's a cyclic structure. It is a planar. So a planar structure is there, and it has complete conjugation in the ring. Electrons are circulating in a cloud, right? So it is there, and the number of pi electrons is also 4n plus 2, right? N is 1. When the number of pi electrons is 6, that means it is obeying the Hugel number, 4n plus 2. So if there is a cyclic system, and that is also planar, and the complete conjugation is also there, right? Similar to aromatic compounds up to here, up to the third one. Cyclic, planar, and complete conjugation is there in the ring, but the number of pi electrons is not 4n plus 2, but 4n. If the number of pi electrons is 4, they are called anti-aromatic compounds. They are not aromatic because the Hugel number is not there. But all these other requirements are there. Cyclic, planar, complete conjugation is there, and the conjugated pi electrons are circulating, but the number of conjugated electrons are not 4n plus 2, but 4n. So they are called anti-aromatic. And what are non-aromatic compounds? So one of these things could be absent in them, right? You don't have to consider the number of pi electrons, because if the system is not cyclic, or if it is not planar, or complete conjugation in the ring is not there, they are non-aromatic compound, right? So you don't have to consider the number of electrons even. But still they can be diene systems, or systems with conjugated double bonds, right? But somewhere the conjugation is broken, right? Maybe a cyclic system is there, but somewhere the conjugation is broken due to the presence of a sp3 carbon atom. Not all carbon atoms are sp2. So let's take some examples to get this idea clearly. Do you have any questions? Hari prashna tiyinawada? Okay. Can you all hear me?
Yes, madam.
Okay. Let's take some examples. Now I have selected very famous examples. These examples, these compounds, you can see in any textbook on aromaticity, or this standard textbooks or in papers also, you get these examples. So I have carefully selected those things, those compounds for you, the structures for you, so that you will get the clear idea how to categorize compounds as aromatic, non-aromatic, and anti-aromatic. Let's take one by one. I hope you have gone through the book and you have some idea, but without wasting time, we'll see so that you can get the idea clear. Right. So this is my first compound. It has a cyclic structure. Right? Nitrogen, they are not all the atoms in the cycle are carbon, but there's one nitrogen atom and the rest are carbon atoms. So you have this structure. So what can you see? What can you say actually? It is a cyclic structure, correct? Is it planar? 4-membered ring. When you make a model with stick and ball with these models, you get a planar structure with 4, 3, 5, 6, 7 up to 8. They are planar, almost planar, right? 8 members even planar structure. Is complete conjugation is there in the ring? What can you say? Can somebody tell me whether the complete conjugation, you know what complete conjugation is? The 5-electron system should be continuous.
Usually I don't see very much of the.
Yeah, why?
Because there is a lone pair of electrons outside.
Yeah, that can be considered as again an electron system, 2 electrons contributing to the system, because this is on lone pair is non-bonded, not bonded. So that can be conjugated with this double bond. 2 free electrons. The problem is here, this carbon atom. It is not sp2 hybridized, it is sp3. Now, though it is these 2 electrons and there are 1 pi bond, 2 5 electrons here, conjugation is here. From nitrogen to this carbon atom, they are conjugated, but there's no conjugation with this carbon atom because there are no 5 electrons or known pairs of electrons here. It is sp3 hybridized. So the some atoms in the ring are sp3 hybridized, does not form a closed shell, right? The electrons cannot circulate right around the ring. It is broken. So this is absent. This is so here when you are checking for the aromaticity, go according to this order. Check whether it is cyclic and then whether it is planar and then whether the complete conjugation is there. Then finally, if the conjugation is there, check for the number of 5 electrons, right? And this is not applicable. There are 4 electrons, but we don't have to consider it, right? So this is not an aromatic compound. And since no conjugation is there, not an aromatic compound, not an anti-aromatic compound, but a non-aromatic compound. Understood? Okay. So the next one, the structure. True, it has a cycle, 5 carbon atoms and 1 nitrogen atom, but there are no lone pairs of electrons because it has a positive charge. But still, the ring has 2, 3, 5 bonds. That means it has 4 of 6 p orbitals where each p orbital is having 1 electron. So that the cyclic nature is there. And since it is a 6-membered ring, it is a planar structure. Complete conjugation is there because all the atoms are, all the carbon atoms are sp2 hybridized and nitrogen is also forming a double bond here. And it forms a closed shell. So 5 electrons can circulate in the cloud. Closed shell. Right? Not open, closed shell. And let's see the number of 5 electrons. It is 6. 2 here, 2 here, 2 here. 6. So it fits into this 4n plus 2. When n is 1, 4 into 1 is 4 plus 2 is 6. So it obeys Euchre rule so that the compound is aromatic. Right? So the next one, again, a cyclic. You can see it is cyclic, right? And it is planar because 5-membered ring. And complete conjugation, you can see now only this carbon, nitrogen is forming a double bond. This has 2 single bond, and the rest of the electrons are here as free electrons. Lone pair of electrons are here, right? And on nitrogen, right? So again, it can form a closed shell of electrons. Can you see 2 pi electrons, 2 pi electrons, and 2 electrons, lone pair of electrons on nitrogen, forming a circle of pi electrons. And the number of pi electrons, 2 here, 2 here, and 2 here, altogether 6. And it is the Euchre number, so it is again aromatic. Right. Next one. 7-membered ring, still cyclic. It is a cyclic structure and planar. 7-membered is going to be still planar. And complete conjugation. Check whether the complete conjugation is there. For that, you have to consider a little phenomena here. When you have a oxygen double bonded to carbon, it can, the electrons can, since the electronegativity of oxygen is more, electron can be more attracted towards oxygen, giving rise to a condition like this. Minus charge on oxygen and plus charge on carbon, and there will be a low, empty p orbital created like this. So what happens is, now you have pi electrons, 2 pi electron here, 2 pi electrons here, 2 pi electrons here, and an empty p orbital here. So that initially we couldn't see that this carbon atom can form any cyclic pi system. But due to this electronegativity of the oxygen atom, it will get an empty p orbital generated like this. So that electrons, pi electrons, 6 pi electrons can move round the ring, including through this empty p orbitals. So that is what it is mentioned here. sp through hybridized carbon atoms and an empty p orbital forms a closed shell of electrons. Right? So that complete conjugation is there. Count the number of pi electrons, 3 double bonds. So that Euchre number, again, aromatic. Okay, all aromatic compounds. Okay, look at this one. This is actually a 1 ring, not 2 rings, 1 ring, but it is cyclic system is there, but it is not planar. Because you know why? When you make the model of this compound, you can see due to these 2 hydrogens, this is going to be buckled. This molecule is going to be buckled, like bent, right? Not a planar molecule, not on one plane, right? So it is not a planar compound. So when the planarity is not there, you don't have to consider the other 2 things even, right? So this does not form a closed shell because it is not planar, right? No planarity. That is not there. You don't have to consider the number of pi electrons even, because from this point, there's no aromaticity. You if these conditions are fulfilled up to here only, you have to consider the number of pi electrons, because if the number of pi electrons are not 4n plus 2, it could be anti-aromatic. If it is 4n, anti-aromatic. But this is not going to be anti-aromatic even, because it is not a planar, no conjugation, complete conjugation in the ring. So it is a non-aromatic compound. Okay, let's see another next example where you have 2 rings, 2 monocyclic. Now, in our explanation, we were telling for aromaticity, it has to be monocyclic like benzene. But there's a small deviation here. It is not a monocycle, but 2 rings. But you have to consider the outer ring of the molecule, right? When you consider this ring. Don't forget about the double bond, the single bond here, but right round you have a cyclic system, right? And it is a cycle, and it is going to be planar because when you actually make the molecule, it is planar. Now you have a question of finding out whether it is planar or not in those examples. The thing is, when you go read the text material, you can come across these examples, and these are very famous examples for you to understand the aromaticity. So you will be get familiar with structures with this type of way which are planar, right? Otherwise, it is very little difficult to predict whether it is planar or not. Right. So the complete conjugation. Now you can see outer ring has conjugated double bond system. All the peripheral carbon atoms are sp2 hybridized, forms a closed shell of electrons. And number of carbon atoms. What is the number of not carbon atom? Pi electrons. 1, 2, 3, 4, 5. Pi means 10 pi electrons. So when n is 2, n is equal to 2. 2 into 4 is 8, plus 2 is 10. So 10 is a Euclid number, 4n plus 2 number, and it is aromatically. Okay, understood? Any questions? Okay, the next example is a 3-membered ring. Now you should be able to check for these requirements. Is it cyclic? Tell me whether it is cyclic.
Yes, it is.
Yes. Is it planar?
Oh, yes.
Yes. Does it have the complete conjugation?
Yes, ma'am.
Yes. How?
There is a lone pair of electrons. Therefore, it
Yes.
can.
Yeah, lone pair of electrons there, and pi bond is here, 2 pi electrons, and lone pair of electrons, so forms a closed shell. And what is the number of pi electrons?
6.
How?
2, 3.
How do you get 6? 4.
4. Sorry.
4. Pi bond, 1 pi bond here, 2 lone pairs. So total number of electrons in the ring, in the closed ring, the number of electrons contributed to form the ring is 4. 2 here, 2 here, right? So 4 is what? Not the Euclid number. 4 is, 4n is, when n is 1, 4n, right? No 2 here. Number 4 is, it obeys 4n rule, not the 4n plus 2 rule. So if it is 4n, what type of a compound is this?
Non-aromatic.
Huh?
Non-aromatic.
No, anti-aromatic, not non-aromatic. It is cyclic, planar, conjugation is also there, and only difference is the number of pi electrons. So it is anti-aromatic. If it is 4n, anti-aromatic. If it had been 6 here, 4n plus 2 is there, it is aromatic, but 4n plus 2 is not here. Only the total number of pi electrons is 4. So it is anti-aromatic. So if the number of pi electrons is 8, it is anti-aromatic, right? And 12 electrons, anti-aromatic, when all the other conditions are fulfilled, right? Okay. So let's take this example. So to make things easy, I have put this one also. So tell me whether cyclic. Now it has, see, it is a positively charged carbon here. And when you have positive charge, that means electron is left. 1 electron is left from the carbon atom. So it has 1 empty d orbital. Positive charge means one empty p orbital is here. So whether it is, see, check, tell me whether it is cyclic.
Yes.
Yes. Planar.
Yes.
Yes.
Yes. Complete conjugation.
Yes. There
Yes,
is-
ma'am.
Yes. Because you know now the reason. 4 pi electrons here and an empty p orbital. So it can form a closed shell of electrons. Electron or Asya, right? Okay. And number of pi electrons?
5 electrons. 6.
Yes. Pi electrons. Or pi plus 5 electrons, including lone pairs.
Yeah, actually, in this case, there is 6 of them.
Now, what is the 5 electron number? You have 2 double bonds.
Double bonds is 4.
4, right? 4. This is empty p orbital. You have 4, but these 4 electrons can circulate because of these empty p orbitals. So, what is this compound then?
Anti-aromatic.
Anti-aromatic, right? It is anti-aromatic. Okay. So, with that, we'll stop our discussion on aromaticity, anti-aromaticity, and non-aromatic compounds, right? So, hope with those examples, you can work out any problem with the considering the number of electrons on the structure and checking whether it is cyclic. Cyclic, you can straight away see whether it is planar and whether the complete conjugation is there, and then finally check for the number of pi electrons. Okay, so we'll see the reactions of benzene. Now, at the start of my day school, I was telling that we are going to learn about the reactions of benzene and substituted benzene. Now you know, you have learned at your A levels and A levels, benzene is undergoing substitution reactions, not addition. Why? Look at this. You have benzene, and benzene is an electron-rich place. You have 3 pi bonds. So 6 pi electrons are concentrated in this ring. So it is a electron, density of electrons is more. So they can be donated to electrophile, species which likes electrons, right? So these electrons in the ring can be donated to this one. So that if the benzene ring is undergoing substitution, something like this should happen, right? So donated, and this electrophile is getting attached, and each carbon atom has hydrogen here. Though we have not drawn, each carbon atom has a hydrogen here, right? So that hydrogen is done like this. And you get a positively charged carbon atom here, if this substitution is taking place. This is not going to take place because this situation is very unstable. Now, if this happens, now you can see this is a very unstable state, whereas it is from a very stable benzene stage, it is going to make a very unstable compound like this. And here, the final product has no aromaticity at all. It has 2 pi bonds, but no complete conjugations here, right? So from a very stable state, the product is going to be a less stable state. So this reaction does not happen at all. So instead of substitution, benzene is undergoing not addition. Sorry, I was mentioning the wrong word. This is addition actually. Double bonds open up and the electrophile adds, right? So addition does not take place at all. But actually, what is the reaction the benzene is undergoing is substitution. You know, substitution is replacement of an atom, right? Addition is double bond is opening up and getting the species added, right? No addition is taking place, but the substitution, and because substitution will give you a stable state again, which has an error, which retains the aromaticity. Right. here I missed this, right? So this one, as I have explained, product of electrophilic addition, aromaticity is lost, no aromaticity here. So this won't take place. Now this product, after electrophilic substitution, again, it retains aromaticity is acquired, right? So benzene is undergoing substitution, but not addition reaction. So you can write the intermediate resonance structures like this. And here you can see, instead of all three structures, you can draw a structure like this, which we call the intermediate pi complex, carbocation, and not pi complex, sigma complex, right? This is called the sigma complex. So sigma bonds are shown here. Pi bonds can be indicated with a dotted line, dotted circle like this, because all these structures have the positive, slightly positive charge on all carbon atoms like this. But as I said, since the electrons are to represent all three structures, you can put a half ring like this and a positive charge here, right? So these things are all there in the book. You can go through them carefully. And let's see the type of reactions you have to learn. Though all these are very familiar, all these 1, 2, 3, 4, 5 reactions are very familiar to you. You have either studied at A levels or the foundation course. What are the reactions? This halogenation reaction, nitration, sulfonation reaction, Friedel-Crafts alkylation, Friedel-Crafts acylation. This is an acyl group, alkyl group, sulfonyl group, nitro group, and halogen. Halogen can be any chloro, bromo, iodo, anything, right? So you are familiar with the set of reagents for each reaction. So we are not going to discuss those things because you can read the book and understand. You already know with your previous knowledge, you know how to write the mechanisms for those reactions. Let's see what is happening with substituted benzene, right? Now, we were talking about the reactions of benzene itself without any substituent. See, think that, consider the benzene substituted with another group, right? Like this. So if this Y is a substituent, right? If this substituent is pushing electrons towards the benzene ring, to the benzene ring, as I have indicated with this red arrow, Y is pushing electrons to the ring. Now, you already know this benzene ring is an electron-rich place. Density of electrons is more. So, it pushes electron, and the electron density is going to be higher than the earlier benzene ring, right? So, there are groups which can donate electrons like this. This Y has a lone pair of electrons which can be donated to the ring. So by donating the electrons also, the electron density of the benzene ring goes up, right? So in cases where either Y can donate it, pushes electrons, or donate electrons, the electron density of the ring is finally increased, right? So in a situation like this, what happens is benzene ring is more activated because it has more electrons that can be donated to any other group, right? More electron density is more by the pushing and donating, right? So the opposite of this is electron pulling, right? So Y group, if the Y group is pulling electrons like this, it reduces the electron density, or else it can remove electrons like this. This double bond can be opened and the electrons are donated towards the substituent. So by both phenomena, by both actions, the density of the ring is decreased. So that benzene ring is deactivated. So you know the reasons, the factors which activates the benzene ring and deactivate the benzene ring. So when you are writing reactions of substituted benzene, you have to find out whether the substituent group is pulling electrons or pushing electrons, or donating electrons or withdrawing electrons, right? So I have an example here, question here, exercise here. Give the structures of the major products of the following reactions, right? So if Y is nitro, what is happening? What is happening when electrophile is attacking the benzene ring?
If it's the nitro group,
Yeah, you consider now nitro group. You have to know what is done by nitro group, NO2 plus group, whether it is pulling electrons or pushing electrons to the ring, or pulling electrons from the ring, or donating electrons to the ring, or withdrawing electrons. Right, each and every, you have to consider the ability of making the benzene ring activated or deactivated by each of these groups. Find out whether nitro group is going to activate the ring or deactivate the ring. Whether bromide group is going to activate the ring or deactivate the ring. Likewise, consider the structures of the substituents and find out. So if I give this as an activity now for you to do now, it will take some time. I will explain what is happening, taking one by one. So suppose this nitro group is attached to the benzene ring as a substituent. Now you are asked to predict the activation or deactivation of the benzene ring when this group is attached, right? So when Y is the nitro group, you know, when you read the book, you can see nitro group can have charge separation like this, right? So the possibility of whether the electron movement or electron pulling or pushing, when you consider the electron pushing or the pulling of the group, you can indicate it like this because of this charge separation, and this one, oxygen is more electronegative and a double bond here. More possibilities to pull electrons because positive charges they are on nitrogen also. So it pulls electrons or removes electrons from the benzene ring like this. So when you write the resonance structures, you get a positive charge migrated to the rest of the carbon atoms in the ring like this. And finally, to get now these are the resonance structures of this nitro group, nitro substituted benzene. And you can see the benzene ring is, what happens to the benzene ring now? It pulls electrons from the ring and ring is deactivated. And you can see ortho and para positions. This is ortho, this is para, this is ortho. Para positions are more deactivated now. So only possibility of the electrophile to get attached is the meta position, right? Because that is the only position which is not deactivated. So it will give a substituted product like this. So only thing you have to do is to find out whether, first you have to find out whether the substituent group is activating the group or deactivating the group. If it is deactivating, find out if it is deactivating, actually these ortho and para positions are more deactivated. So less deactivated position, only place left is meta, so that deactivating groups are going to give you meta substituents, right? So next example.
Meta?
Yes.
About the last resonance structure, is it a triple bond with between nitrogen and
Sorry. Yeah, good for pointing it out. It has to be a double bond, right? By mistake, I have made it a triple bond, right? Like this, right? This oxygen should be the same thing. Only the double bond system should be the other way around. Same, the original position should be there. I have made a mistake here, right? Minus charge on oxygen and a double bond here, right? So it has to be like this, minus triple bond here, double bond here, right? Okay, so good for pointing it out. Okay, next example, OCH3. Now you can see OCH3 is the electron donating group. You have a lone pair of electrons on oxygen. So it donates like this, and ortho and para positions are more electron rich. More density of electrons are more on ortho and para positions. So the ring is generally activated, and ortho para positions are more activated, so that you can get either an ortho product or a product. Right? You can see now the similar examples are there in the book. I'm just showing you what is happening, whether it is activating or deactivating, and you write all the resonance structures and see how it is getting activated, how the ring is getting activated, and the positions which are going to get more activated, right? And this one, here you have to consider two factors. Halogen atom is more electronegative. Electronegative atoms pulls electrons, right? So that due to pulling, it shows electron withdrawing inductive effect. Minus I effect is electron withdrawing mesomeric effect or inductive effect. So when the electrons are pulled, ring is deactivated because the electron density is going to be lesser than the benzene ring. And again, halogen atoms have non-bonded electrons like this, right? 6 non-bonded electrons. They can be donated to the ring. So by that way, it is activating the ring, right? So when you write the resonance structures for deactivation and activation, when you are considering the overall activity, overall effect of the withdrawing and donating, non-bonding electrons can be donated to a lesser extent to the ring, right? So the compound is orthomera, deactivates the ring because of due to this one, but still it is orthopara directing. This action is more due to this electronegative factor has to be considered more, and it is deactivates the ring, but still it is orthopara directing. You will come across so many examples here in your course material explaining this, and you have to consider it is activating and orthopara directing. And deactivating groups normally activates the meta position, but here you have to consider both effects, and activate the deactivating effect is more, but still it is orthopara directing. Right. So these examples, I don't think that I have to go through them. Predict the major products of the following reactions. You read the book and you will come across these reactions, and you will just see whether these groups are what is the substituent groups. Now benzene, these are special reactions not coming under this the 6 types of reactions we have learned at A levels. Now this is actually a sulfonyl group which deactivates the ring. So the bromine addition, when it is deactivating, you know, meta addition will take place. Like that, you decide the place where the second substituent is going to get attached. And when you have 2 substituent, now this is activating and the other one is deactivating. So consider the effect of both substituents and what happens to nitrogen, right? So okay, I have the explanations here. Actually, this is a Friedel-Crafts alkylation type reaction where you have OH instead of a chloride. The reagents has to be changed, selected accordingly when it is an alcohol. So with benzene, you can attach the substituent to any position. But when you have substituted benzene, as I said, this is deactivating and meta-directing. This compound, deactivating and meta-directing. And OH is activating because it has oxygen has lone pairs of electrons. they can be donated to the ring, right? So that it can activate the ring. Now this is deactivating because pen is not writing. Okay, now this carbon, you have the carbonyl group. So oxygen is more electronegative. The bond can open towards the oxygen side, so that these electrons are moving